All right, let's continue with Christofide's algorithm here. Christofide's light is like to joke around. A couple sort of loose ends to wrap up. So conceptually, if you look at the last video, we kind of did a concrete example of going from a minimal spanning tree to an Euler cycle to a Hamilton circuit or Hamilton cycle, right? So let me outline that. So minimal spanning tree to Euler cycle to Hamilton cycle. Okay. Contained in these issues are being careful with the edges you use, especially in this last step, to be aware that if your graph violates triangular inequality, make sure you take the shortest route. Okay? Otherwise, the whole point of this can get ruined. All right, so let me show you kind of first of all, a sort of a geometric-ish or kind of an idea with a visual of how this process can be visualized. So if you think about it, just draw yourself a tree. You can kind of doodle your own if you want. Pick your favorite. I don't want to get too extreme here. Okay, and so just for argument's sake, to make it kind of appropriate to this, consider this tree to be a minimal spanning tree. All right. All right, so the next thing you can do is this Eulerization process can kind of seem haphazard, and it is in the sense that you can make choices and make these twisted, but there's sort of an untwisted version. So there's kind of a way of doing this Eulerization that is kind of neat looking. So you can think about it as this, is just taking a walk around the tree. And you start looking at it, it's like, okay, well, every edge got doubled up, got double used, right? If you were to collapse this path onto the edges that are there. But if you move them just slightly off the graph like this, this taking a walk around the tree is kind of neat. All right, now, kind of the last step here is, so take a walk around the tree. The last step is if there's someone you've been, you got to jump to somewhere you haven't been. So, I need to draw the same tree. Otherwise, let's get too messy. This is quite visual. I don't know if it's very algorithmic. But functionally, this is what you're doing. So if this particular walk around the tree is your Euler cycle, it's one of many options, but it's a neat geometric option. Then what you can do is you can kind of do this process. You can say, all right, if I'm going to use the walk around, I can actually use orange because the pink is darkish. Let me use orange so it stands out. All right, so I can think about the idea of the Euler cycle, but I'm going to create a Hamilton cycle now from this idea. So I'll start walking around. What I don't want to do is come to an edge. So now I'm going to have the option of going around back, but I've used that edge, right? So what I need to do is I need to jump to the first thing that I haven't been to. So in this case, not that one, but that one. Right, so not that. It's now geometrically, you can see, hopefully this, that was a little aggressive for me to jump right into the graph. So I'm going to continue there. What you can see is a triangle, right? And hopefully this direct route is at least not longer than this one. Right? And of course we can assure that by making sure we use Dijkstra's to figure out the route from here to here. And it's not going to be any worse than this minimal spanning tree route there. All right, continue on. All right, and anytime you get to a leaf, you never want to backtrack along that edge that got you there. So you're going to have to jump somewhere next. And I don't want to go back there because I've been there, but I haven't been to that one, so I'll go to that one. Okay, and then I go around. And again, I'm at a leaf. So I don't want to go there because I've been there. I've been there. So that's the next one I'm going to do. So I'm going to go here. Now, I don't want to go down because I've been there. There. So anyway, from here, go there. close it off. Okay, and so think about it this way, right? Which of these edges, which of these orange rubber bands is the longest? Well, if this was geometrically accurate, and I did a little more than I had to here to add some sort of bumps, this second attempt is shorter than that one, right? And this is kind of the geometric appeal of Christofide's algorithm. It doesn't have to be done in exactly this way, but this is one way of doing Christofide's algorithm among all of the options available. Because your options actually change and become diverse once you realize you have a bunch of different Euler cycles. And this particular way of doing this is one of two ways to create an Euler cycle. I can actually do this. This is counterclockwise, or I could go clockwise and do this. So if you want to do an attempt yourself, try doing this clockwise. Check it out. Don't think you get the same. You don't get the same end result, which is neat. And then you can actually twist and right. You don't have to. You can think about actually taking this tree and giving it a twist, right, and doing different things. So there's a ton of Euler cycles available. Okay. So this orange, the cost is equal to 2 times the cost of the MST. This thing's cost, if the triangle inequality is honored, or I use Dijkstra's algorithm properly, is less than or equal to 2 times the cost of the MST. Okay, this is kind of the book's end goal, to create a result using their branch and bound, which has some of the flavors in here, but their algorithm to me is way more complex and difficult to execute. What's important here is to note that if you want to do Christofides in its full power, there's an extra step about making sure these leaf jumps are optimized. Okay, so there's a process for that. Okay, but if you kind of use the light version that uses just taking it this far, this is what we get. Okay, so let's kind of encapsulate all of this. Okay, so Christofide's algorithm, first of all, its steps is you find MST, minimal spanning tree. 2, Eulerize. Right, lots of options available. And then step 3, remove redundant vertex visits. Use Dijkstra's, is it? Yeah. As needed. Right, so anytime you have to leave the tree to go from vertex to another, just use Dijkstra's, it's much safer. It will help you honor the triangle inequality. Okay, so as a result, we get this theorem that, how do I want to say this? Okay, consider a connected weighted graph G. Okay. And parenthetically, and its completion. G bar, and I'm going to add a little triangle to note that we also replace any bad edges. This is just so we can refer to this thing. Okay. A Hamilton circuit, or cycle, whichever one you like. I say both, I guess, a lot now. I used to always say Hamilton cycle. A Hamilton cycle exists that costs less than or equal to 2 times the cost of a minimal spanning tree. Okay, and then this notes Hamilton cycle is on this completion, but we often think about it as practice, as this completion really is just a data encoder for ways to visit vertices on G. So if you want to kind of put this Hamilton cycle on G, it's just a cycle that visits all the vertices. It's just the best we can do, right? So it probably loses its distinctive name. Hamilton cycle just becomes a cycle. But from a verbiage standpoint, keep in mind, we are doing a Hamilton cycle problem on the completion, and we're using this on the regular graph G. So you don't have to completely jettison the name. Just be careful about its usage, really. That's what's important here. Okay, if you look up Christofides, this can be improved a little bit. But keep in mind, there's one loose end here. And that is, what would be the minimum cost? I mean, what's our basement's cost of a Hamilton cycle? And this is just good for kind of contextualizing our result here. Is it actually a decent result? Well, it actually is. The cost of the minimal spanning tree is actually a lower bound for the cost of a Hamilton cycle, any Hamilton cycle. And in fact, it's a strict lower bound. The reason why it can't be equal to is because if it, well, I couldn't say if it was because that's going to be a contradiction, is think about a Hamilton cycle that's as cheap as possible. Right, if I remove one edge, and if it was cheaper than a minimum spanning tree, then I have a cheaper tree that was cheaper than the minimum spanning tree, contradicting the minimal spanning tree being minimal. All right, so the cost, this is true of all Hamilton cycles, it's greater than the cost of the minimum spanning tree. It's a little close. Let me just write this one more time. The cost of any Hamilton cycle is always greater than, strictly greater than, because there's going to need another edge to pull this off, a minimal spanning tree. Right, if the cost of a Hamilton cycle was equal to the cost of a minimal spanning tree, you or I could create a spanning tree that's cheaper than a minimal spanning tree. So there's no way they could be equal. This has to be one edge more expensive at least. Whatever one edge more expensive might mean. Maybe it's a unit or whatever unit to measure you're using. Okay, so this is pretty good, right? We know costs of cheap Hamilton cycles are greater than a minimal spanning tree, and we're keeping it less than 200% of that. So it's not a bad result. This is a really good place to start. And you can typically do a good bit better, but anyway, that's a discussion for a little later. All right. So I think that's it for this one, and I'll see y'all on the next one.